Hai semua, Assalamualaikum dan salam sejahtera. Untuk kuliah pada kali ini adalah masih lagi berkisahkan tentang pengimejan digital, tetapi kali ini saya akan ceritakan berkenaan radiografi digital ataupun digital radiography DR. Seperti sebelum ni yang telah saya terangkan, di mana CR kita menggunakan kaset yang di dalamnya ada plate pengimejan. Tetapi untuk DR, kita tidak menggunakan kaset, tetapi kita menggunakan flat panel lepeh ataupun flat panel detector. Okay. Kalau kita tengok pada gambar ini, ada dua jenis flat panel, iaitu direct dan indirect. Okey, saya akan terangkan berdasarkan video-video yang akan dipaparkan nanti berkenaan dengan DR dan juga bagaimana proses kerja modaliti DR di jabatan, ya.
In this video, we'll be covering cassetteless digital radiography systems. Cassetteless digital radiography is different from CR radiography in that there is no cassette or imaging plate reader. Cassetteless digital radiography can be broken down into either direct or indirect systems. Indirect radiography can be further broken down into either thin, flat panel transistors called TFTs or charged coupled device systems called CCDs. Indirect TFT systems are composed of three main layers: the top scintillation layer, a middle photodiode layer, and the bottom TFT array. The top scintillation layer or light layer is where the incoming incident X-ray photons are converted into light photons. A scintillation is nothing more than a burst of light, which is why this layer is called the scintillation layer. Each photon that strikes the scintillation layer creates a small burst of light energy. Unfortunately, one downfall of using a scintillation layer is that it produces light isotropically, or in all directions. The isotropic nature of this layer thus acts to decrease spatial resolution, since the converted light photons are of a greater size than the incoming incident X-ray photons. Basically, the scintillation layer creates a small amount of blur on each image. The scintillation layer is comprised of either the ionic compound cesium iodide or the chemical element gadolinium. Cesium iodide is preferred over gadolinium since it can be formed into very small rods. These small cesium iodide rods are able to produce a smaller, more focused light beam, which in turn serves to increase spatial resolution. After the scintillation layer comes the photodiode layer. The photodiode layer is comprised of a semiconducting material known as amorphous silicon. The photodiode layer works by converting the incoming light photons from the scintillation layer into electric charge. The electric signal or electrons produced by the photodiode layer are then transferred to the thin film transistor or TFT layer. The TFT layer is comprised of an array or matrix of very small detector elements, or DELs for short. Each DEL is comprised of a capture element or pixel detector, which is the active element within each DEL. A storage capacitor, which stores the electric charge produced by the capture element, and a thin film transistor or switch that acts to open and close the release of electric charge leaving each DEL, thus producing the digital image. The ability of each DEL to produce a high spatial resolution radiograph is designated by the percentage of the active pixel area within each DEL. The percentage of DEL to active pixel is known as the fill factor. There is a direct relationship between fill factor and spatial resolution in that as the active area increases, that is, takes up a greater percentage of space within the DEL, spatial resolution increases. The charge coupling device, or CCD system, is the other form of cassetteless digital radiography. CCD systems differ from the TFT systems in that with the CCD system, there is no photocathode or TFT layer. The scintillation layer within CCD systems are optically coupled to each CCD sensor chip by either lenses or fiber optics. The CCDs are able to both convert light photons into electrical signals, as well as send the electrical signals to the computer for processing. The final cassetteless digital radiography system is the direct conversion radiography system, or non-scintillation system. This system is comprised of an amorphous selenium-based semiconductor and a TFT. This system works by applying a high voltage charge to the top surface nanoseconds before the X-ray exposure is made. The interaction between the incident X-ray photons and the high voltage charge causes the selenium atoms to release their electrons, which are then able to be collected and processed by the TFT layer. This final image gives a visual illustration of each type of cassetteless digital radiography system.
Hi everyone, so for today's topic, we are going to talk about the indirect flat panel system. And before we go further into the discussion, I would like to briefly explain what exactly is a flat panel system. It is actually an image receptor that is used in digital radiography system. What it does is that it converts X-ray light into electrical charges, which then will produce an image in digital form, which is a metric of pixels, each with a numerical value. Finally, a digital image will be displayed on the monitors. So we go dive deep and understanding how does the process work for indirect flat panel system. And without further ado, let's get started. Just like I mentioned earlier, the indirect system has a two-step process. The first one is that the X-ray photons will be converted into light, and the light photons will then later be converted into electrical charge. This flat panel system consists of phospholayer such as gadolinium oxysulfide and thallium dioxysium iodide. The scintillation layer can either be structured or unstructured, but unstructured will produce more scattered light, hence reduce the efficiency of detector. It also consists of photodetectors such as hydrogenated amorphous silicon. The digital sign is read out by thin film transistors, TFTs, or charge-coupled device, CCDs. Now this is the difference between structured and unstructured. As we can see from the diagram, unstructured indirect flat panel system uses CCDs, while structured uses TFTs. Next is the TFT layer. So the first layer is scintillator. It is made of a cesium iodide. Its function is to convert X-ray to visible light. The next layer is photodiode. It consists of amorphous silicon. It converts light to electrical signal. The last one is a thin flat panel transistor, or TFT. The function is readout signal and will produce digital image. Moving on to the next one is CCD. The scintillation layer within the CCD system are optically coupled to each CCD sensor sheet by either lenses or fiber optic. CCD are able to convert light photons into electrical signals and send the electrical signals to the computer for processing. So how does it work exactly? Well, firstly, the X-ray photons reach the scintillator. The scintillator then convert X-ray into visible light. Visible light produced is proportional to the incident energy. The visible light is then converted into charges. Then, it will convert to electrical charges by a photodiode array. Lastly, the charges is read out by thin film transistor array, or TFT. There are a few advantages when it comes to indirect flat panel system. The first one is that it has an active readout, meaning the image viewing is immediately. It also uses more compact technology, has a shorter acquisition time, and it uses discrete detector element. But of course, there are disadvantages as well. Using the indirect method, It first converts X-ray energy to light prior to electrical signal. This will cause a risk of blurring caused by the scattering of light photons.